Here we have the differential equation y double prime minus 8y prime plus 20y is equal to 100x squared minus 26x e to the x. This looks pretty innocuous, but it's going to turn out to be rather involved. We do start out first with the auxiliary equation, which in this case is m squared minus 8m plus 20 is equal to 0. We can go quadratic formula on this, but when the coefficient of the quadratic term is 1 and the linear term has an even coefficient, I find it to be just a lot quicker to complete the square. So I'm going to subtract 20 from both sides. Cutting 8 in half gives us 4. Square that 16, so we're going to add 16 to both sides. The left-hand side factors into m minus 4, the quantity squared. The right hand is negative 4. Square rooting both sides, and then isolating m is going to give us m is equal to 4 plus or minus 2i. That gives us a complementary function. Y sub c is equal to e to the 4x times the quantity of c1 cosine of 2x plus c2 times the sine of 2x. At this point, we do need to double check. Compare that complementary function with the right-hand side of the non-homogeneous differential equation. We see that this is a second-degree polynomial for the 100x squared, and negative 26x e to the x is the product of a linear and an exponential function. None of those is the product of an exponential and a cosine function, so there's no duplication of terms here. There's no what I would call redundancy here. If there was, we'd have to find out how to deal with that, but what this means is we can proceed using the technique we used before. I'm going to, again, split this up into two forcing functions. We're going to consider the 100x squared, which is a second-degree polynomial, and then identify that yp1 should be a second-degree polynomial, ax squared plus bx plus c. There are steps, of course. They take a little bit of time. You can verify if you want to pause it and work on it right now, go ahead, but I'm just going to go ahead and write down that yp1 in this case is going to be 5x squared plus 4x plus 11 over 10. Because I'd like to focus more on the second part of it, that negative 26x e to the x. This is the product of a linear function and an exponential function. Therefore, I'm looking for y sub p2 that has the form of a product of a linear and an exponential function with coefficients to be determined. Yeah, we are actually guessing the form of solution, but in kind of a protected situation here. Folks, a linear function is not just x. A linear function has a linear term and a constant term. I want you to think about equations of lines. Y equals mx is not our general linear equation. It's y equals mx plus b. So we should have two terms here. And so for the linear part, I'm writing down ax plus b. I'm going to multiply that, so I'm going to wrap it in parentheses. And then for the exponential part, e to the x, we're just going to write down e to the x. And you may wonder, what happened to the, like an a or a b or a c in front of e to the x? It doesn't matter. When we distribute, we have the undetermined coefficients in each term. So this is actually sufficient for us. Now, the bummer of this is, to find the derivative, we have to use the product rule. So yp2 prime is going to be, I'm going to do this two ways. We're going to use the product rule here, and I'll just reference like ax plus b is the one underlined in blue, e to the x is one underlined in green, so I'm going to reference it using the colors. Blue prime is a, and then green is e to the x, plus blue, which is ax plus b, times green, which is e to the x. And then if we want to, we can collect some like terms here, and we have a plus b e to the x plus ax e to the x for our first derivative. As an alternative, when you have an exponential, it's going to show up in every term when you're using the product rule, because whether you differentiate it or not, you have that exponential, right? So I'm going to do this kind of like in, I guess, a bit of a slick way. I know e to the x is going to be in every term, so I'm just going to write it down like over here as e to the x. And then I'm going to think of this as like blue prime green plus blue green prime, but knowing that I've factored out the e to the x. So the blue prime, ax plus b prime, is a. And we know that would be times e to the x, but we've already factored it out. So plus u, which is ax plus b, times e to the x, but we've already factored that out. And you might find that to be a useful, oh, that should be a prime. You might find that to be a useful way to differentiate functions that have exponentials in them when you're using the product rule. In fact, we're going to do that again. yp2 double prime is, okay, so we actually have a product here, right? A plus ax plus b times e to the x. Using the same colors, because hey, it worked before, I have blue times green, blue being the polynomial, green being the exponential. We know when we use the product rule, we're going to have e to the x in all the terms, so I'll just write down e to the x out here. And then we're going to consider blue prime is simply a times green, well, we already have the e to the x out here, plus u is the blue one. That's a plus ax plus b times green prime, but we already have the e to the x there. So this allows us to write down, 2a plus b plus ax and all that times e to the x. Take your pick at how you actually do that. Now, this is going to go into the differential equation, but we've tunnel visioned it, right? We're only looking at the exponential part. So this is going to go into y double prime minus 8y prime plus 20y equals negative 26 e to the x. And yeah, this is a lot. But y double prime is 2a plus b plus ax e to the x minus 8y prime, which I've written as a plus b plus a to the x all times e to the x, plus 20y, so plus 20 ax plus b e to the x, is equal to negative 26x e to the x. And as we saw before with an exponential, there's an exponential in every term. So we get to divide that out. It's non-zero. Then I'm going to set an equation just of the constant terms and an equation of the linear terms, I guess the x terms. Constant terms are 2a plus b. Don't forget to distribute the negative 8. So we got here 2a plus b minus 8a minus 8b from the next function here. And then we have here plus 20b. And on the right-hand side, there's no constant term, so it equals 0. For the x terms, again, on the left-hand side, we have ax. I'm not going to write down the x because we can see that there are x's everywhere, right? Negative 8ax, so I'll just write that down as negative 8a. And then 20a on the left, so plus 20a. And on the right-hand side, the x term, neglecting the e to the x, is negative 26x, so I can write this down as negative 26. Based on that last equation, we can get that a is equal to negative 2. And then backing into the previous equation, we then find that b is equal to negative 12 over 13. Putting it all together, we have that y is equal to e to the 4x times c1 cosine of 2x plus c2 sine of 2x plus, so that was our complementary function. And then the one we didn't go through, but you know how to do, 5x squared, 5x squared plus 4x plus, what was that, 11 over 10? Yeah. And then plus our new thing. Now, our new thing had the form ax plus b times e to the x, where we found that a was negative 2 and b was negative 12/13. So this is going to give us plus negative 2 minus 12/13 e to the x. And that's the solution to our non-homogeneous differential equation.